All right, the last thing I'm going to talk about with buffers and titrations is a little bit about how indicators work. Okay, remember earlier when we talked about you can use a pH meter for a titration, you can also use an indicator. And the way that an indicator works, is that it changes color when you reach what's called the end point, which is very, very close to the equivalence point. But how do indicators change color at a point very close to the equivalence point of a titration? The answer lies in what is an indicator. Okay, an indicator is also, like most titrations, is also a weak acid. Okay, and just like with a weak acid, we abbreviate a weak acid by writing HA, where the A stands for acid. You can abbreviate an indicator by writing HIN, where the IN stands for indicator. And so an indicator, like a weak acid titration, also contains an acid and a conjugate base. Okay, so in terms of like phenolphthalein, phenolphthalein, when it's in an acidic solution, so think about your pH curve here. Okay, when it's down in here, phenolphthalein is clear. But once you get up into here, phenolphthalein changes color to pink. Okay? So how does it do that? Well, if this is phenolphthalein, again, when it's in an acidic solution, it's clear. Okay? So, and that means when you have more of the HIN version of phenolphthalein, it's clear. But as soon as you start to have more of the conjugate base form, it turns pink. Okay? So an indicator changes color when there's more moles of the conjugate base than there are moles of the original acid that was present. Now, when does that happen? Think about a titration. At what point in the titration, again, don't think about the indicator here, think back to the titration. At what point here in our titration do you now have more conjugate base than you do acid? The half equivalence point, right here. Okay, so you got to be really careful because it's almost like there's two titrations going on here. There's a titration that you're actually worried about, this big titration here, but at the same time, the indicator is also undergoing a titration where slowly over time, the acid is turning into the conjugate base. Okay, the problem is they don't coincide exactly with each other. Okay, because where do we want this color change to happen? We want the color change to happen as close to the equivalence point as we can. Okay, and so therefore, when do we want that clear to turn to pink is right there. Okay, but in terms of the indicator, at what point in the indicator's titration are we? And this is where it can, again, be a little bit confusing, but hopefully I'll clear it up here. Okay, in terms of the indicator, we want the indicator to change when we want it to turn pink when the actual titration is at its equivalence point. But at what point in its titration is the indicator? It is at its half equivalence point. And we know that at the half equivalence point, the pH is equal to the pKa. Now, what does all that mean? It means that when you are trying to choose an indicator, how do you know what indicator to use? Okay, you want an indicator that changes color as close to the equivalence point as possible. And the pH at the equivalence point should be as close to the pKa of the indicator as possible. Let me say that again. You want the pH at the equivalence point of the titration to be as close to the pKa of the indicator as possible. And again, why is that? Because again, that's where we want the color change to happen. We want the color change to happen when the indicator is at its half equivalence point, when now there's more of the conjugate base than there is the acid. Okay, so the half equivalence point of the indicator is we want that to be as close to the actual equivalence point of the titration. Okay, so we want the pH of the solution to be as close, so this is the pH of the solution, to be as close to the pKa of the indicator, because remember, the pKa of the indicator at the half equivalence point is equal to the pH, right? Remember, at the half equivalence point, the pH equals the pKa. So at this point right here, we are at the equivalence point. What's that pH? We don't know, but we want that pH, again, to be as close to the pKa of the indicator as possible. Okay? So let's just look at an example, see if that clears it up a little bit. Let's say we've got this titration curve right here. Okay, and again, we can estimate, we know that the equivalence point is happening at 25 milliliters, but then we're going to take we're right about there, and we're going to come back over, and we're going to say, the pH at the equivalence point is pretty close to 7, okay? It's actually a little bit higher than that. I kind of combined two different questions together. So we're just kind of say it's pretty close to 7. It's just a little bit above 7. So the pH at the equivalence point is just barely greater than 7, but it's very close to 7, okay? So at the equivalence point, okay? If that's the case, what is the best indicator for determining the endpoint? So remember, the indicator is the one where, again, it's going to change color when it's at its half equivalence point, where the pKa equals the pH of the solution, of the indicator solution. So if the equivalence point is very, very close to 7, we want to choose an indicator that has a pKa also very, very close to 7. Because we know that when the pKa reaches the point where it equals the pH, then that's when the color change is going to happen. So the indicator, the best indicator we could use for this one would be bromothymol blue. Okay? If the equivalence point didn't happen until up around the 9 area, then the pH at the equivalence point would be close to 9, and we would want to choose an indicator whose pKa is close to 9, and therefore phenolphthalein would be a good one. Let's say we did a different one. Let's say we did a base one where we started up here and it went down, and let's say the equivalence point, again, let's say it was around, 3. Okay, which could happen, certainly could. Okay, let's say that at the equivalence point, the pH is around 3. What indicator would you use then? The one that has a pKa closest to 3. Okay, which in that case would be thymol blue. So again, you want the pH at the equivalence point to be as close to the pKa of the indicator, because again, the pKa of the indicator indicates the point at which you're switching from having more of the acid to having more of the conjugate base, and that's when the color change happens. When you have more of this, again with phenolphthalein, it's pink. When you have more of the acid, it's clear. So when the pH at the equivalence point is close to the pKa of the indicator, that's when you're going to see that color change happen. So again, these are pretty easy questions. You just find the equivalence point, and then you find the indicator that has its pKa closest to the pH at the equivalence point.